All right, open up your book to section 7-4. We're on page 357 in your book, and the title of this section is Arcsine, Arctangent, Arccosine, and Trig Equations. And the objective here in this section is to find algebraically or numerically the solutions to equations involving your circular or trig functions, that is sine, cosine, and tangent, of one argument. And you may recall in the last chapter, we've already covered what arccosine is. So we will refresh our memory on that, but we aren't going to go any further into arccosine. But the two new ones here for us are arcsine and arctangent. We will definitely dive deeper into those two. All right, so let's start out with a little refresher here from section 6.6 actually. If you need to go back and check over your notes to refresh your memory, or go back over the video that you've watched already to refresh your memory on these, or maybe even look over some of the problems from your assignment, then do so. But this is what we learned in section 6.6 was about arccosine, dealing with the inverse cosine relationship. And it turns out that arccosine can be defined in the following way. Remember that what we're doing is solving an equation that looks something like what you see here on the board. We've got cosine of x is equal to a. And if you're trying to solve an equation like that, when we first started working with our inverse trig functions, we solved those by using cosine inverse. And we got one solution. And that one solution was between 0 and 180 degrees, because that's the range of the inverse trig function. That's the restriction we make on the original function so that it becomes invertible. But now what we were looking for in section 6.6 was looking for all these solutions. If you think about what your cosine function looks like and you set it equal to a value between -1 and 1, there's actually an infinite number of solutions. And so if I want to find all those solutions, cosine inverse, that function cosine inverse, doesn't quite cut it. So this is defined as the inverse cosine relationship. Remember, that's the key there. It's a relationship, not a function. A function, plug in one input and you get one output. A relationship, that's not necessarily the case anymore. In fact, that's definitely not the case here. When I plug in one value, I'm going to get an infinite number of possible solutions here. So we defined this function arccosine. So from now on, to solve or rewrite a problem that starts out with cosine of x equals a, we said we're going to write x equals the arccosine of a. And then we defined arccosine of a in terms of cosine inverse, but it was plus or minus cosine inverse, so we have two solutions there to consider. And then we added on multiples of 2 pi. That's multiples of the period that we're adding on there, so because this repeats every period. So plus 2 pi n, where n is some integer. This gave us all of the solutions. And then we looked at how to determine whether I used the positive or the negative cosine inverse and what values of n to pick to get the right solution. Again, go back over your notes there, go back to that video there if you need to refresh your memory on how to do all that. You should know how to do that at this point in time. All right, let's take a look at an example here. We'll start out with an example similar to an example that we started out with in section 6.6, and see if we can actually come up with how to find all these solutions. We want to find all the solutions to this equation, sine of x is equal to 0.6. All right, so if we sketch this y value of 0.6, we'll say 0.6 is maybe about right here. That might be a little bit too high, but it'll be close enough for what we're trying to do here. We'll call that 0.6. And you can see that we've got actually an infinite number of solutions here. Here's 1, here's 2, here's 3, 4, and obviously this would continue moving off to the right, finding more and more solutions, and obviously it would continue off to the left, the same thing. So there's an infinite number of solutions here that we're seeing. And we want to come up with all these solutions. So let's think about how we would solve this problem originally, that is using just our inverse trig functions, and then use that to help us come up with how we'll find all these solutions. So let's take sine of x equals 0.6 and write down that equation. And what we first learned when we were learning about our inverse trig functions is we said that if I have sine of x is equal to 0.6, I can rewrite that as x is equal to the sine inverse of 0.6. Those two statements mean the same thing there. Now, it's a big restriction on the domain here that you're dealing with, but those two statements do in fact mean the same thing for us. However, this only gives us one solution. And which one solution is it going to give us here? When I look at this sketch up above, I've got 6 of them marked here, but obviously there's an infinite number of them. Is it one of these solutions, or is it one that I don't even have marked that I'm going to get with that sine inverse solution down below? Well, to answer that question, you got to think about the range of this sine inverse function. We initially defined the range of these inverse trig functions in degrees, because that's all we had learned at that point in the last chapter when we learned radians, and we started working in radians more and more. And so this problem here is also in radians because I'm using x. I'm going to go ahead and write this range in terms of radians, but obviously it's the same in degrees there, just do the conversion. So the range that we found out for sine inverse is that its range was from negative pi over 2 to, oops, right, put a parenthesis around this, I guess, to pi over 2. So that turned out to be the, if we're sketching an angle in the first, or in the standard position there, that's in the first or the fourth quadrant, is what we're talking about there. So that's the range of my inverse trig function. So which one of these solutions is the one that I'm going to find? Well, if that's the range of my inverse trig function, remember the range is the same as the domain of the original function. So we're talking about the domain from negative pi over 2 to positive pi over 2. So I got to go back and refresh my memory here about this trig function and maybe perhaps a little bit on radians. But at pi over 2 is where my my sine function hits its high point, and at negative pi over 2 is where it hits its low point back here. There's our negative pi over 2 and positive pi over 2. So if you will, we could kind of sketch maybe a line here and a line here right through that high point. That right there is the range that we're talking about for sine inverse. If you calculate the sine inverse of any value, you're only going to get numbers as a result that are between negative pi over 2 to positive pi over 2. So with that, we can clearly see which solution we're going to find. It's this one right here. That's the only one that falls in that interval. So that's one solution. But again, I'm not going to be happy with just one solution. I want an infinite number solution. I want all the solutions. So how do I get the rest of the solutions? Well, if we look carefully at what we've got here, there with this function, there's some nice symmetry that occurs. In fact, the same thing occurs with your cosine function as well, but our ranges are different. So on this function here, when I look at the solution I end up with and the symmetry, there's some nice symmetry that shows up here. In fact, if I were to mark this distance right here horizontally between the y-axis and that solution I'm looking for, that distance that I'm looking at there is actually what sine inverse is telling me. It's telling me that x value right there. That's the distance I am from the y-axis. This is sine inverse of 0.6 actually. Tell me how far that is. Another way of looking at that is if I were to mark on my x-axis here, this point right here that I've got marked, that is the sine inverse of 0.6. All right, those two things are telling me the same thing there. If I were to mark at pi, this is pi right here. If I were to mark a line here at pi, I guess I can do in both directions, but I only really need the top part of this. If I look at this line at pi and measure this distance, you should notice that we've got some symmetry here. Some symmetry about this point at pi over 2, this high point, that this solution I'm looking for on the left is the same distance from that high point as the one on the right. So that means that this distance that I just marked here is also sine inverse of 0.6. Those are both measuring the same distance there. So then the question is, well, how do I use that to find out then what the coordinates of this x value is right here? That's what I'm trying to find. I want to find those two solutions, those two values of x. Well, you can measure, maybe I'll do this in a different color here just so it's a little bit easier to see. But if I were to measure the distance from the y-axis over to that purple line that I sketched, that distance is pi. And then if I subtract off this distance that we were just talking about up above there as the sine inverse of pi, sine inverse of 0.6, the difference between those two is going to give me the location of this x value. Again, I'm measuring a distance that's too big, and I subtract off the little bit that I don't want, and I'm left with the quantity you do want. So it turns out then from that, I should be able to say that this x value right here is pi minus sine inverse, erase that a little bit, minus sine inverse of 0.6. There are my two solutions. Now that unfortunately does not rewrite as neatly as I saw with arc cosine, that it could be a plus or minus cosine inverse. It would be really nice if I could write it that way for this one, and unfortunately I can't. So let's write this in a piecewise form here. Actually, let me erase this x equals, and we'll rewrite this in a piecewise form. So I'm going to put a little piecewise function here, and we'll say x equals this piecewise answer. One solution that we already know is sine inverse, and the other one that we just came up with then, because of the symmetry, is pi minus sine inverse of 0.6. There's our two solutions. Now those are the two solutions on this first little upper bound that we've got sketched here. But I can see if I move over to the right, I've got even more. There's two more over here and two more after that. Those repeat every period. So if I just add on multiples of the period, I'm going to get all of these solutions. So the period of our sine function is 2 pi. So if I tell it to add on 2 pi n, and add on 2 pi n, just like we have defined for our arc cosine, we end up with getting all of our solutions. This looks like our method that we'd use to find all solutions. Not only that, but I should also know what values of n to pick, and whether it's the sine inverse or the pi minus sine inverse solution, to get any particular solution. For example, let's do this. I'll do this in this orange color here. If I look at the phase displacement for my sinusoid, in this case it's 0. I'm subtracting 0 from x is what I've got there. That tells me my starting point for n. So unlike arc cosine, we were looking at where the upper bound was, because that's our location of the phase displacement. That's our d value. For sine, the d value, the phase displacement, is where you're crossing the sinusoidal axis and you're increasing. So this right here is where n is equal to 0. So it looks like we're going forward from there to find that first solution. You're moving to the right. That's the sine inverse solution. And it looks like if you continue moving forward, you'll find the next solution is your pi minus sine inverse solution. Those are the two that we wrote down below there, our sine inverse solution and our pi minus sine inverse solution. If I continue with that, here would be where n is equal to 1. If I go to the right, this is going to be the sine inverse of 0.6 solution. And if I continue moving to the right, this next solution I hit is the pi minus sine inverse solution of 0.6 for n equal 1. And this would continue then. Here's where n is equal to 2. This first solution that I hit as I move to the right, this is my sine inverse solution of 0.6. And as I continue moving to the right, the next solution I hit is my pi minus sine inverse of 0.6 solution. So again, it's not a guess and check here of figuring out what value of n do I pick, and is it sine inverse or is it pi minus sine inverse to get that. You should be able to look at that sketch and know immediately, if I want that fifth solution that I see here, that fifth positive solution there, that's n equals 2, and that's the sine inverse solution. That's this guy right here. For any one solution, you should be able to look at it immediately and figure out what value of n to pick and whether you're using sine inverse or pi minus sine inverse. So that actually brings us to our definition here, similar to what we just had for arc cosine. The definition of arcsine, that's the inverse sine relationship. Again, remember, this is a relationship. It's not a function. When I plug in one value, I don't get just one value out. I'm going to get an infinite number of solutions here as I plug in different values for n or pick the sine inverse versus pi minus sine inverse. That's going to give me an infinite number of solutions. In particular, all of the solutions is what we're looking for. So from this point forward, when we're solving an equation involving sine, like if sine of x is equal to a, Once you get it to that point, we're not going to just simply write down sine inverse of something, but rather we're going to write this in terms of arcsine. We're going to say x is equal to the arcsine of A. If you have sine of x is equal to A, our next step is x equals the arcsine of A. And we'll keep that in the problem until we simplify it completely for the x. In this case, it's already there, but sometimes there's other stuff you got to get away from the x that's in this problem. But once you finally solve it for x all by itself, then you can replace arcsine with what it's equal to. And what is it equal to? Well, it's what we just came up with. We just came up with this on the other slide there. We found out that the two solutions that you're going to find in the first period are at sine inverse of A and pi minus sine inverse of A, and that they repeat every 2 pi. So we add on 2 pi n to each of those. Now with arc cosine, we had a nice way to write this, and we could do it without a piecewise form. But however, remember that when we were solving these out, many times at the end, we would rewrite it in a piecewise form because sometimes you're using different values of n for the positive cosine inverse as opposed to the negative cosine inverse. In this case, you always have to write it this way. There's no other way to write this. It's got to be written in the form of a piecewise answer. And it makes it a little bit easier then to remember that you have to indicate values of n for the first part and values of n for the second part. All right, so there's our definition. This is in terms of radians, but of course, if you wanted to convert this over degrees, just remember that you got to convert everything to degrees. So the pi that you see in the second part of this, pi minus sine inverse, that has to be converted over 2 degrees. That's 180 degrees minus sine inverse. And of course, the 2 pi, that's 360 degrees. You got to replace the 2 pi n's with 360 times n. So you can do a conversion from radians to degrees here, but you got to make sure you convert everything from radians to degrees. If you forget the pi that's out front, then you got a wrong answer here. All right. Let's look at this a little bit more closely and go back and refresh our memory here on both the domain and range of our sine inverse function. As you go about solving these equations algebraically, which is going to be the major task that we've got to accomplish here, understand how to solve these algebraically. Recall what the domain and range of your inverse sine function is. Remember that the sine function itself is not invertible. So we've restricted its domain from negative pi to negative pi over 2 to positive pi over 2. Or that's a negative 90 degrees to positive 90 degrees is what we saw initially when we did that. We restrict its domain, so now it becomes invertible. That domain now becomes the range of our inverse function. So the range of sine inverse is from negative pi over 2 to positive pi over 2. That's quadrants 1 and 4 if you're sketching this as an angle in standard position. And the corresponding range then of the original sine function becomes the domain of our inverse function. So the domain here is from negative 1 to 1. So the values of A that you can plug into that sine inverse function there are from negative 1 to 1. All right. So with the fact that there are 2 quadrants to consider, quadrant 1 and quadrant 4, I do need to consider what happens here, or at least go through with you what happens here, if we're dealing with an angle that is in the first quadrant, that is it's between 0 and positive pi over 2, versus the fourth quadrant, that is it's between 0 and negative pi over 2. What happens there? So let's look at an example. The good news here is the example we've already looked at is what happens if it's in quadrant 1. But let's go through this and make sure we're clear, and then we can kind of use that to help us see how we apply it to the quadrant 4, what happens if the angle's in quadrant 4. So I'm going to pick A to be some positive value. I'll pick it to be some value up here again, we'll say. So we'll call that A. So when you go to find your solutions, again, remember that the range of this function, what we just went over, here's negative pi over 2. Here's positive pi over 2. So the range here of your sine inverse function is the domain restriction that we made here on this function. So I can see that the solution you're going to find is this solution right here. just like we saw on the previous slide. And furthermore, we can figure out what values of n to pick and whether I'm using sine inverse or pi minus sine inverse to get these solutions. Again, your starting point, you look at your phase displacement. So when I look at this equation here, I'm not subtracting anything from x. That is at 0. So x equals 0 is where n is going to be equal to 0. That's my starting point. And then I move forward from there, move to the right to find that first solution, because that's the only one it's going to find there, from negative pi over 2 to positive pi over 2. That's going to give me my sine inverse solution. So this is my sine inverse solution. I'll write it down here. I'll just call it sine inverse. If I continue from there, the next solution that I'll hit is the pi minus sine inverse solution. I'll just write it as pi minus sine inverse. Oops. If you want to put an a, I guess we could put an a in there since that's what we're dealing with. You could write it that way. There's those two solutions. And this continues moving forward from here. If this is n equals 1, then the first solution that I hit right here, that's the sine inverse of a. And continuing to the right, the first solution you hit, this one right here, that is going to be the pi minus sine inverse solution. And again, here's n equals 2. Moving to the right, the first solution we hit, that's our sine inverse solution. And then the next solution you hit as you go to the right, that's the pi minus sine inverse solution. All right. Again, that example we started off with, that should hopefully look very similar because that's exactly what we did there for that first example. Nothing new there. The question is, what happens if we are in the fourth quadrant? So let's consider an example that illustrates that. So if we're in the fourth quadrant, that means we're talking about a value of a that is negative. So sine of x equals a, where a is less than 0. All right, so let's sketch that. So a is going to be less than 0. A is negative. That means it's down below the x-axis here. So let's sketch it something like this here. We'll say that's our value for a. This is a here. And so again, if you think about your range of your sine inverse function, the range is from negative pi over 2 to positive pi over 2. So we're talking about this window right here. We've restricted our domain down to that, and the sine inverse is going to tell us the one solution in that domain, which is clearly down here. So that's a little bit tricky here then, and the fact that if we go back again to sketching where n starts, look at your phase displacement for your sine function. It's, again, got a phase displacement of 0. That is, it's x minus 0, x minus d. The d value is your phase displacement. So the phase displacement on sine tells me where I'm starting, where I cross the sinusoidal axis and I'm increasing. So that would be right here at the origin then. This is where n is equal to 0. The thing that's a little bit different here is that notice to find that first solution, I actually have to go to the left to find it. That solution right there is the solution with n equals 0, and this is the sine inverse of a solution. This is when a is negative. And where's the other solution? Where's pi minus sine inverse? Well, sine inverse here, remember that's an x value we're talking about, that's a negative number here. So if I take pi minus sine inverse, pi minus a negative number, I'm going to get an answer that's bigger than pi. So where exactly is pi? Well, pi is actually, do that in a different color here. Pi is actually sitting right here, right? This is pi. So we're talking about an answer that's bigger than that. And again, if you think of the symmetry that we're talking about here, it'll help you see why this is the case. But the solution that we're talking about finding then is this one here. In other words, you don't keep going back to the left to find the other solution. This one that's further over here to the left that we've got marked is not the other solution for n equals 0. So one of them is off to the left here, and the other one is off to the right. If I head in this direction right here, this will give me the pi minus sine inverse solution. Pi minus sine inverse of a. And this continues. Let me do this in a different color just so it's easier to distinguish between these. If I make this n equal to 1, now when I go backwards to the left, this is going to give me my sine inverse of a solution. And where's the other solution? I got to go back to n equals 1 and then move to the right from there. So that's right here. This is my pi minus sine inverse solution. And I can find the last one here. Go back to red here. Here's where n would be equal to 2. If I go backwards, this is the sine inverse of a solution. And I don't have it marked, but if I had it marked, I'd head in this direction to find the other solution. Again, it shouldn't be a case of you just randomly picking values of n and randomly choosing between sine inverse versus pi minus sine inverse to find all your solutions here. We should be able to determine what our solutions are knowing this right here. Right, the tricky part of this is to know that the value of a is positive, you're going to the right to find both solutions. If the value of a is negative, you're going to the left to find the first one, but you always go to the right to find the second one. That's the difference between these two. Both answers are to the right here for quadrant 1. One answer is to the left, one answer is to the right of your sinusoidal axis for this solution. All right. Let's look at an example here, but let's talk about interval notation because the example we're going to talk about has this in it. The problems that you're going to work with, they'll mostly give you an interval notation that you're going to work with to indicate what solutions they're looking for. And so the set notation that you see over there on the right is what you're going to see show up. But if you want to rewrite it as an inequality, in fact, many times I'll probably write it that way instead, you can write it that way. That first inequality that you see there is 0 less than or equal to x less than or equal to 10. That's talking about all values between 0 and 10, including the 0 and the 10. So over on the right there, you can write this in a set notation. The way that you read this little guy off here when you say x in this kind of E-shaped thing, this is read as x is an element of. X is an element of, so x is an element of the set from 0 to 10. And the key there is that the square brackets are used when you're including endpoints. So you can see here that I've got x is less than or equal to. I'm including the endpoint there. So I've got a square bracket that I'm using there to indicate that. The same is true here on the right, that I've got x is less than or equal to positive 10. And so I'm using a square bracket there. All right, take a look at the next one here. I've got 0 is less than x, which is less than 10. So now, when I'm using just less than, like I see here and like I see here, now I use parentheses to indicate that I'm not including those endpoints. Square brackets, you're including the endpoints. Parentheses, you're not. So x is an element of the set, the open interval from 0 to 10. The square brackets, we use the term closed interval. Parentheses, we use the term open interval. You don't have to necessarily use those words there, but those will sometimes be used to describe those. And of course, you could vary these now. The next one is 0 is less than x, which is less than or equal to 10. So I'm including the 10, but not the 0. Notice that over there on the right. You can have a parenthesis on one side and a square bracket on the other side, just like you can have less than on one side, but less than or equal on the other side for an inequality. And the same is true for the last one. 0 less than or equal to x, which is less than 10, is the same as saying that x is an element from 0 to 10, including 0, but not 10. Okay? So those are interval notations that you'll see with some of these problems. All right, let's try on one of these examples here. Take a look at example 1. Example 1 says to solve the equation 10 sine of x minus 0.2 equals a negative 3. And they want me to do this algebraically on the domain from 0 to 4. Now here they didn't use the set notation, used the inequality notation, but again, I'm showing you both there so that way you can realize they're the same thing. But you could say x is between 0 and negative 4, including that, or you could have said 0 is an element of the set from 0 to 4, including 0 and including 4. So we've got square brackets. Those mean the same thing. All right, so to solve this, actually, before we solve this, we could actually find the right values of n and the sine inverse or pi minus sine inverse, or know those values before we even start. So let's do that, actually. Let's graph what this function would look like. Now you do need to have an accurate sketch of this because you need to know how far this 0.2 phase displacement that you're putting in here, how far is that going to shift that over to the right, all right? But once I have an accurate sketch of that, this is going to look something like this, right? That is, this starts here at 0.2. That's what that phase displacement of 0.2 is going to do. So the first period there actually ends here at not 2 pi, but this is really 2 pi plus that phase displacement of 0.02. So that's where that's at, and then this is actually at 4 pi plus 0.02. Again, our phase displacement gets pushed in there, and everything gets shoved over to the right there a little bit. All right, we're trying to find out where this function is equal to -3. Again, this is an amplitude of 10. And so -3 would be somewhere down here, we'll say. This is -3. And so you can see there we've got our 4 solutions here that we're looking for. Here's 1, 2, 3, and 4. Now one thing you do have to watch out for, you got to be careful of, is to know for sure what solution you need there, whether the way I've got this sketched here, I could sketch this a little bit further over on the left. You know, the question that I've got here is where exactly does this intersection occur at? If that intersection occurs to the right of the y-axis like I got sketched, then I want to include that one, which means I would not include the one at the very end. All right? Otherwise, if it crosses to the left of the y-axis, then the opposite's true. Okay, so I do have to have an accurate sketch. I do have an accurate sketch here right now, but just realize that you do need to know exactly where that first intersection is at in terms of the y-axis. Sometimes we need an accurate sketch to know that. But those are the 4 solutions that we're going to look for. So the phase displacement they gave us here, this is n is equal to 0 right here. And since we're setting it equal to a value that's below our phase displacement, below our sinusoidal axis, that means that we're taking the sine inverse of a negative number. So that means that this first solution that I would get with sine inverse is actually the solution that I erased there. So this solution right here is the pi minus sine inverse solution they'd end up with n equals 0. Here's where n would be equal to 1. This solution that I hit back here is going to be the sine inverse solution. And the one over here is going to be the pi minus sine inverse solution. And finally, here's where n would be equal to 2. And this right here is the sine inverse solution for that. So again, before I even did the work here, I know what answers I'm looking for. If you ask me for any one of these particular answers, I could tell you what I've got to use in terms of my final answer at the end, whether it's sine inverse or pi minus sine inverse, and what values of n to pick. You don't have to start out the problem with that, but I just wanted to demonstrate to you that it's not a case of you get to the end and then you go, well, I have no idea how to pick the right answer. You should know how to pick the right answer from the very beginning. All right, so let's take our equation then. 10 sine of x minus 0.2 is equal to this -3. Go through and solve this the same way that we've solved these with cosine in there. First step is to divide by the 10, so I've got the sine of x minus 0.3. Oops, that's 0.2. Is equal to a -3 over 10. I'll leave it just like that. You could write that as a -0.3, I guess, would be fine to do. Maybe that would make sense to do it that way since I've already got a decimal in here anyways. And now here's where we use our arcsine here for this next step. I'd have x minus the 0.2 is equal to the arcsine of a -0.3. And I'm going to keep that in the problem until I finally get x by itself over here on the left. So add the 0.2 and we'll be there. So 0.2 plus the arcsine of a -0.3. And finally replace now arcsine with what it's equal to. Remember, this is going to be a piecewise form. So I've got a 0.2 out front. I've got to add that in there, plus the top part of the definition is the sine inverse of a negative 0.3. Again, we already said we're taking the sine inverse of a negative number. We knew that to start off with, plus 2 pi n. And then we've got that 0.2 that starts off in there already, plus pi minus sine inverse. Here's the definition of arcsine, plus the 2 pi n. And now all I need to do is figure out what values of n to pick and whether I'm using the sine inverse or pi minus sine inverse. But we already did that, actually. Let's go back up to our sketch. We already did that work to start off with. For the sine inverse solution, here's n equals 1. That's one solution. And there was n equals 2. So we need n equals 1 and n equals 2 for that sine inverse solution. And for the pi minus sine inverse solutions, pi minus sine inverse with n equals 0, here's one solution. And with n equal to 1, there's the other solution. So we need 0 and 1 for those values of n. All right, hopefully that looks a lot like the problems that you've already done with involving arc cosine, and that there's not a lot that's different here. But nonetheless, that's the technique we're using to solve these problems. That right there is the end of the first half of section 7.4.